Welcome to the Peacademia course on the basics of semiconductors. This lecture covers the Avalanche and Zener breakdowns in PN junction diodes. Let's start. By the time you finish this lesson, you will learn the PN junction reverse voltage tolerance, Avalanche breakdown, and the Zener breakdown. In previous lectures, I explained the PN junction behavior under the reverse biasing. We all observed that a PN junction significantly limits the current flow when it is reversely biased. In this lecture, my intention is to talk more about the PN junction operation under the reverse bias, and I'm primarily looking for an answer to this question. What if I apply a large reverse voltage over the PN junction? Here is a PN junction which is reversely biased. The reverse voltage applied to this PN junction repels the minority charge carriers from the two ends of the device. What I mean is that electrons as the minority charge carriers of the P semiconductor are repelled from the P semiconductor metallic contact, and the holes as the minority charge carriers of the N semiconductor are repelled from the N semiconductor metallic contact. As a result of this repulsion, these minority charge carriers go within the diffusion boundary. From now on, they are affected by the depletion region electric field, sucked in the depletion region, pass through it, and end up in the other side. This movement of minority charge carriers makes the reverse saturation current. So far, everything looks normal, and nothing has deviated from what I explained in the lectures that were about the reverse biased PN junction diode. Now, what I want to do is to significantly increase the reverse applied voltage. To put this into perspective, imagine that at first the reverse voltage was 10 volts. Now I'm giving it 100 volts, 10 times larger. What happens now is really interesting. Everything that I explained earlier in this lecture remains correct. However, a detail is added to the process that changes the outcome. Like before, the minority charge carriers are repelled from the metallic contacts, go within the diffusion length, sucked into the depletion region, and finally go to the other side. The difference here is that as a result of the huge electrical field caused by the large reverse voltage, the minority charge carriers gain lots of kinetic energy. For example, consider an electron as the minority charge carrier in the P semiconductor. When it arrives at the N semiconductor, it collides with an atom in the N semiconductor. Because the kinetic energy of this electron is so large, it causes a covalent bond to break. Therefore, a new hole and electron are generated. This does not end at this point. The initial kinetic energy was that large that part of that energy is now given to the new generated hole and electron. The new electron collides with another atom, and that causes one more covalent bond to break. This process goes on and on. What we can see here is that an electron is causing too many other electrons to get generated in the N semiconductor. It's equivalent to an avalanche in mountains. As a result of this avalanche, the concentration of minority charge carriers increase drastically. We already know that the reverse current is proportional to the concentration of the minority charge carriers. Now that we have increased the concentration of charge carriers a lot, the reverse current skyrockets. This process is called avalanche breakdown. Under this condition, the reverse voltage was already very large. Now the reverse current gets very large too. So the power lost in the device becomes huge. Under this condition, the device can be damaged permanently. The reverse voltage at which the avalanche breakdown happens is called the breakdown voltage, and shown by V sub B. You already saw this normalized current density voltage diagram for the PN junction in the previous lectures. What I did not show in this diagram was the avalanche breakdown. If I increase the reverse voltage applied to the PN junction diode, I get to a voltage at which the reverse current skyrockets. This voltage level is the breakdown voltage V sub Bi. Now is the time to ask a very important question. What determines the breakdown voltage in a PN junction? Well, the breakdown voltage to a large degree depends on the doping concentration, as shown in this diagram. The smaller the doping concentration, the larger the breakdown voltage. In other words, the larger the doping concentration, the smaller the breakdown voltage. Therefore, we can conclude that V sub B is disproportional to the doping concentration. When the subject of the discussion is the avalanche breakdown, we need to secure some time to discuss the Zener breakdown too. The Zener breakdown is named after the American physicist Clarence Zener, who first described the Zener effect in 1934. Unlike the avalanche breakdown, to achieve a Zener breakdown, we need a highly doped PN junction. When the doping concentration is very large, the depth of the depletion region gets smaller, and the electric field in the depletion region becomes much stronger. As a result, even with a small reverse voltage applied to the PN junction around a couple of volts, the electrons are directly removed from their covalent bonds, and therefore pairs of free electrons and holes are generated. In this lecture, I discussed the ideal PN junction reverse voltage tolerance and avalanche and Zener breakdowns. In the next lecture, I will explain the junction capacitance. Thanks for joining this lecture of Peacademia.